share the screen. Can you see my screen?
Yes, sir.
All right. Right. So first thing, so I want to discuss about a question that Rakal asked me. So in class, right? So graph of a smooth function. So why do you need smoothness? So today is 18. So in general, so suppose M is a topological manifold and of course with a homeomorphism phi from M to some Rn, all right, or open subset of Rn. Then n comma phi will give an atlas. So hence it will be manifold. So that means, so that is graph. So if phi, if f, so in particular actually, if f is a function from, let's say, Rn to let's say R, and you look at the set M to be x comma fx, where so it is continuous. X is in Rn, the graph. So here also, so this M is a topological manifold, and phi from M to Rn, so phi x f comma fx will be x, is a homeomorphism. So this M comma phi will be an atlas. So this implies, so M has a differentiable structure. So this is true. So the question was, the theorem was in general, if f is a smooth function, then the graph is a smooth manifold. The catch is much later, so we'll see that. So for example, so an example, so suppose this one. Suppose, right? So you know this. So what is it? Yeah, graph of mod x, right? So the question is it a smooth manifold? Right. So what do you think? Yep.
So here, whole m comma phi is just that one thing is the atlas, that set of one element.
Yeah, that's true. So this will be in itself, if you look at, not inside R2. If you look at just that set and with the map, that gives you a manifold structure. So that is a manifold. But what is not? So this corner is a problem. So this corner is a problem to be a smooth manifold. So in certain case, so generally what we think, so if you, so there is another way to define a smooth manifold is is collection of all something what is called submanifolds of Euclidean spaces. All right. So here, if you look at ambient structure of R2 and induce from there, then it is not a manifold. So that means this set. So if M is x comma y equal to mod x, then M is included inside R2, right? So this is an inclusion map. Now this map is not smooth. So this I is the inclusion map is not smooth. So what it means is that this graph is not a submanifold of R2. So when you look at the ambient space and look at the structure from R2, in that structure it is not a manifold. But you can always give a single chart and say this is I mean give a manifold structure, but that's not compatible with R2. All right, that is the point. That is the point. Firstly, this Aditya wrote me an email saying about these things, but yeah. So whenever we think of a manifold, we generally intend to think inside some Euclidean space, and there the corners are problem. If there is a corner, it is not a smooth manifold, which means it is not a smooth submanifold of the Euclidean space. All right. I hope that will make things clear. All right. So let's go to the tangent space. So is the definition of tangent space clear to all of you? So M, suppose M is a smooth manifold, and P is an M. So what is TPM?
All the derivation at
Yeah,
one time.
at P. Collection of all derivations at P. All right. And suppose F is a map from M to N, M, N are smooth manifold. Then what is this F star? P. This is from TPM to TPN. And how is it defined? F star P acting on VP. VP is a tangent vector in TPM. This should be a derivation. This should be a derivation. Now acting on a function F. Give us what? Function G give us what? Vp, which is the derivation at M at the point P, acting on functions near P. So what will be the function near P? G compose F. All right? Yeah. Is this fine? All right. So this is how things are defined. Now, once it is defined, you can prove chain rule. So what would be the chain rule? The chain rule. Suppose M, N, and P are smooth manifolds. F is a map from M to N, and G is a map from N to P, right? Then so G compose F star, right? P. So P is a point in M. Is equal to, what will be its equal to? What is your guess? Yeah, can you guess? G star of FP composed with F star P. That is the chain rule. So in place of a star in multivariable calculus, you wrote the derivative df, dg compose df, dg at fp compose df at p, right? All right, so how do you prove? Proof is easy, very easy. So G compose F is a map from M to P, right? So G compose F star at P, acting on, will be acting on BP. So BP is from TPM, right? Now this should be a function, this should act on a function of function at P, right? So this is H. Now this is BP of H compose G compose F, right? By definition, yeah, this is by definition. Now you look at G star FP compose F star P, and now this is a map from, of course, again TPM to T G compose F P of capital P. So domain and range are same. Now we apply G star FP compose F star P acting on VP. Now this will be a derivation here in this tangent space. Now you act on a function H at P. H is a function at P C infinity at of course P, and this is G compose FP. Now this is BP. Oh well, so this would what would give you first? This is G star FP of F star P VP, right? This whole thing acting on H, right? Acting on some function H. Now what is this? So how do you see this composition?
Sir, apply F star P VP on H compose
Right.
H compose F
H compose?
H compose G compose F.
No, G. H compose G. Now
G at that point.
this is a derivation. So this is a derivation on N. See, the map was F was from M to N. So this F star P of VP is coming from TPM. So this is a map. This is a derivation on N. So it should be acting on function defined on N. Now this is equal to VP acting on H compose G compose F, right? So these two are equal, right? Simple. So once we define, these things are simple. All right. So this gives you a chain rule.
Sir, 1 second, can you turn back?
Yes.
1 second, can you turn the
Yeah.
Sir, can you explain how did you apply G star on that?
G star on
G
here.
star on that inside part in the second last line, the right side end.
You mean this one? This one?
Yes, sir. How do you apply that?
Oh, this is just a this is just composition of two map, right? That's what I wrote.
No, sir. How do you apply that to the next step?
Oh, from here to here.
Yes, sir.
So this is call this one as WP, right? Call this one as WP. So this is nothing but, let me give it here. So this is G star FP of WP acting on H, right? So what is the definition? Right? So the definition is WP H compose G. Yeah. So this is what we do. This is WP.
Yes, I got it.
Yeah, because this is from where to where. So this should be a derivation on TPN, which is in our case here also. So this is not P. Sorry, there is a little problem here. So this is not P. So this should be at a P. Right. So this is at the same point it should be applied. So this is not P. This is not P. So this is a WFP. All right. Now this is perfect. So it should be at the point FP. The points here and here should be same. That's what we always do. Here FP and this is a derivation at FP. All right. Okay. So what is the differential for identity? Identity map. Differential of identity. So suppose M is smooth manifold and identity is a map from M to M, right? X goes to X, or P goes to P. So what is the differential of identity? So what is identity star at P? Any guess? Hmm? So any guess? What should be? I mean, just a guess. I'll not ask for reason.
Sir, identity itself.
Yeah, but identity. Which identity?
Tangent space.
Right. So identity at TPM. Right? So identity at TPM is a map between two vector spaces, TPM to TPM. All right. So this the proof is simple. So identity star P acting on BP, and then you act on some function F. So what would be BP? F compose identity. So which is BP of F, right? Yeah. So the map identity star P of VP is VP, so which is for all VP in TPM, right? So this is an isomorphism, identity isomorphism. Is this clear?
Yes, sir.
All right. Few more things. So suppose so so corollary of chain rule. If f from m to n is a diffeomorphism, then f star p from TPM to TFP n is an isomorphism for every p in M. Is this clear? So, what is the definition of diffeomorphism? What is the definition of diffeomorphism?
So a bijective map from M to N such that it is C infinity, and its inverse is also C infinity.
Right, right. So, F is so since this is a diffeomorphism, there exists a map, a smooth map G from N to M such that G compose F equal to identity of M and F compose G is identity of N, right? So now, so G compose F is a map from M to M, right? So G compose F star P, right? Which is a map from TPM to TPM. And by previous one fact, this G compose F star P is identity at TPM. And now this one by chain rule is G star FP compose F star P, which is identity TPM. This implies and similarly, so it has F star P has right inverse, and now similarly G compose F compose G, F compose G is identity N, so this would give you F star GP compose G star or GQ, G star Q equal to identity TQM, right? Now GQ, since GQ is P, so assume you can take, right? So suppose FP is equal to Q, and therefore since G is F inverse, so GQ is P, and that will give you GQ is P, so that will give us F star P compose G star FP equal to identity TFP M, right? So this 1 and 2 gives
So that should
some of
be
these.
TP. That should be TQN, right?
Ah, yes, TFP and yes, right. So that gives you 1 and 2 gives us that star P is invertible map. So that gives you uh, is an isomorphism. All right, isomorphism between vector spaces, because linearity part is clear. That we have not shown here, but you can check easily. Yeah, any question till now? So next one will show another way to represent the tangent space. So mostly that will be very useful to look at tangent space in case of manifold inside some Euclidean spaces. So that will be by using curves. But let us start that one after medicine. So it will take some time, and I want almost everybody to be present here because that is also a very important one. Okay. So any question?